In the last video, we discussed how the derivative of a function at a point x equals a denotes the slope of the graph of the function at the point x equals a. In other words, if f is differentiable at the point x equals a, then the derivative there assigns to the point a number, namely the slope, denoted by f prime of a. This means that if f is differentiable at every point of its domain, then we can consider the derivative of f as a function in its own right, mapping a point a in the domain to the value f prime of a. This function, f prime, enjoys the geometric interpretation as the so-called slope function of the graph of f. Let's do an example to illustrate this concept. Consider the function f of x equals x squared, and let's try to find the derivative of this function, f prime of x. The way the derivative is computed according to its definition is the limit of the difference quotient at the point x. Using our description of f then, we find that this difference quotient is x plus h squared minus x squared all over h. Expanding the numerator shows that it's equal to x squared plus 2xh plus h squared minus x squared. Canceling the x squared terms, we find that this numerator becomes 2xh plus h squared. In particular, we can factor out a copy of h, and upon doing so, we can cancel this copy with the factor of h in the denominator. In total then, the limit is equal to the limit of 2x plus h. Since we're taking h to 0, this limit just becomes 2x, which is the value of the derivative. In other words, the derivative is f prime of x equals 2x. Now, the graph of this function is just a line, which we could plot on the plane. We could also plot the graph of the original function, f of x equals x squared, which is itself a parabola. Now, the idea of the derivative is that it is supposed to represent the slope at each point of the parabola. In particular, at the origin, which is the vertex of the parabola is flat, and so the derivative should be 0 there, which it is. However, as x moves to the right, the slope of the parabola becomes positive, which is indeed reflected in the values of the derivative, which become positive as we move to the right along the line y equals x. And as x moves to the left, the slope of the parabola becomes negative, which is again reflected in the graph of the derivative, which is negative to the left of 0. In fact, this derivative provides even more precise information about the slope, not just whether the slope is positive or negative, but rather what the exact value of the slope is. For example, if we look at the point x equals 2, then the slope of the parabola is clearly positive there, but how positive is it? Well, the derivative at x equals 2 has value 2 times 2, which is 4, and so this means that the slope of the parabola is 4 at the point x equals 2. This type of geometric analysis is even possible when we don't have exact values to work with. For example, suppose that the graph of f is given here by this curve. Our goal is to then sketch the graph of the derivative f prime if we can. Now, because we don't have exact values for f, we won't really be able to sketch the derivative with precision, but we can get an idea of its general shape from some key information about the graph of f. In particular, there are certain points along the graph of f where the graph is flat, for example, at the peaks of its curves or at the valley in its center. Since at these points the graph is flat, this means that the slope is 0 at these points, and so the derivative should be 0 there as well. On the graph of the derivative then, we should plot the value of 0 at the points x equals minus 3, x equals minus 1, and x equals 1. But what about the rest of the behavior of the derivative? Well, to the right of x equals 1, the function f has negative slope, and in fact this slope becomes more and more negative as x increases. What this means in terms of the derivative then is that the derivative takes on negative values to the right of x equals 1, and these values become more and more negative as x increases. The story is similar to the left of x equals negative 3. In this region, the slope of f is positive, and the slope becomes more positive as x moves to the left. In terms of the derivative then, its values are positive to the left of 3, becoming even more positive as x moves to the left. The only regions left to examine then are those in the middle. For the left region, that is the region between x equals minus 3 and x equals minus 1, the slope of the function is negative. This means that the derivative should have negative values in this region, so its graph should be a curve lying below the x-axis. In a similar way, since the graph of the original function f has positive slope between x equals minus 1 and x equals 1, the graph of the derivative should lie above the x-axis there. One important thing to note is that because it looks like the slope of f changes gradually, it should also be the case that the values of the derivative change gradually too, meaning that the derivative should be continuous. We've tried to reflect this in the graph of the derivative by keeping the curve a continuous curve. On the other hand, if we change the example so that the function f is now the absolute value function, then we see that its slope does change rapidly. In fact, at the origin, the slope jumps from being -1 to 1, which means that the graph of the derivative should jump from -1 to 1. In this case, the derivative is not continuous, and this is because the slopes of f jump from -1 to 1. In addition, the derivative isn't even defined at x equals 0, because there, the function doesn't have a well-defined slope. There is no single tangent line that approximates the graph at this point.